Okay, so last time there were a couple of questions about the geometry of the dynamical horizon. So I'll just spend a few minutes on that and elaborate a little bit on more on the main result we proved, and then we'll start with the second topic of the course, which is gravitational waves. So we're still just finishing up now. Page 1D, which was dynamical horizons. And yeah, and for dynamical horizons, the idea was that it is a space-like surface, right? Some space-like surface like that. It doesn't have to be complete, so you can start with some two sphere here. This is the topology. There's two here. And then it goes to say, another two sphere. So again, the topology is 2. And the question was about these various vectors. And I think there was some confusion about these vectors. So for dynamical horizon, this is dynamical horizon H. What we know is that the expansion of the outward future directed null normal is equal to 0, and the expansion of the inward future directed null normal is negative. So these surfaces are marginally trapped, and if you move a little bit inside, then the statement is that the area decreases. So that's the reason these are of interest. These are black hole type. These are future directed outward normal, whose expansion is actually equal to 0. And then the question was, how do we? So it is foliated. So dynamical horizon is foliated or sliced by two spheres with this property up here. And so the question was, how do you construct various vectors? So last time what I did was I said, well, because it's a dynamical horizon, it's space-like surface, therefore it has a null, therefore it has a space-like, it's a space-like surface, therefore it's a time-like normal, and so I got time-like normal here, and that is what I got T. And then I also said that I got, it's a space-like surface, and at each point up here, I'm going to have a marginally trapped surface, S2 up here. And so I called this vector up here by R. I guess I said that you need, therefore I put a hat here, T hat and R hat. And then I was just saying that, well, I mean, just by construction it is true that L and N are LA up to normalize, overall normalization, which we choose that L dot N is equal to 2. So I can just write LA to be equal to tau hat A plus R hat A upon 2 plus R hat A and A equal to tau hat A minus R hat A. And then these are obviously null and they satisfy the conditions that we talked about. And L and N by construction are linear combination of vectors which are perpendicular to these two spheres. So of course L and N are null normals. Given any two sphere, there are exactly two null normals, and therefore I found them. But I guess various people were not comfortable with this, and they said, well, but I don't have R, why did you just define this R? Is R really tangential to this surface, etc.? Of course, here by construction, R was tangential to the surface. So alternatively, what we can do is the following. This is what was asked, and this is a straightforward geometry exercise, but I first thought that you guys would just do it, and you probably would do it, but after the class there are other people who also asked me the same question, so I thought I should just elaborate on that. So alternatively, what we have given is this slicing, and therefore we got this LA and NA, which are given to us. Right? L is a future directed, both are future directed. This is outward pointing, and this one is inward pointing. That is what is given to us. So alternatively, what is given to us is really these two null normals, L and A. That is what is given to us. But also I'm given the whole manifold tau, whole manifold which is the dynamical horizon. Therefore I'm also given the null normal to it, tau, right? So I'm given a null normal to the dynamic horizon. That is given to me also. Now L and N, this is equal to 0 and this is less than 0. Therefore, the normalization of L and N up here is not fixed. I can rescale L by f, some function f, and N by 1 upon f, and that is perfectly fine. So the absolute normalization is not fixed up here. So what we do is, given the slicing, I just get null directions, if you like, and you can normalize them against each other by asking L dot N is equal to -2, but still I can rescale each of these null vectors. So it is conventional to just say that, well, you normalize by taking L dot P hat A. So this is given to you, this is given to you. They are both future directed, null and time-like. Therefore, of course, the inner product is negative. So we just normalize it by asking that we normalize tau. Sorry, we're given tau, therefore we normalize L by asking that the inner product is equal to -1. And similarly, NA inner product is equal to -1. We just normalize this. And then, and of course, we also, so we just normalize it in this particular way. And then the statement is that we can just define R hat A. This was the kind of question that was being asked, I think, last time. I can just define R hat A up here by R hat A is just defined to be equal to LA minus NA divided by 2. I can just define this at the moment. So this is what I was doing last time, but we could also just start here, given L and N, I normalize them in this particular way, and then define R hat A. And then the question was, how do I know that this R hat is actually the normal to the surfaces within the dynamical horizons? In other words, how do I know R hat is space-like? How do I know it is tangential to the horizon? So the question is, why is R hat space-like? Why is R hat tangential to H? So these were the questions that we're asking. Right? This is the question that you were asking, right? And so now we just did this construction, so you just do it, right? Just calculate what is R hat A. And this is positive, it's +1. And is it tangential? When you just calculate the inner product between R hat A and T, and tau A is 0. Tau is a normal to, so you can just show, it's two-line algebra, so I think you should do it, is you can just show that R hat A is equal to +1, R hat A is so defined, is normal, and R hat A is equal to 0. Tau hat is a normal to the surface, so any vector which is normal to the normal is tangential to the surface, so R hat A is therefore tangential to the surface. Okay. So you can do either way. I just was doing it one way, which is
Is it obviously normal to the two spheres within the space-like hypersurface too?
it is linear combination of two normals to the two spheres.
Yeah, okay.
So it's also normal to the two spheres. Right? Every vector which is a linear combination of L and N is normal to the two spheres.
Real quick, so the dynamic horizons are they time-like surfaces?
No, they're space-like surfaces.
Space, okay, right.
Actually, for this fast-track course, I'm just assuming them to be space-like surfaces. What one can really do is one can define a time-like trap tube, just a trap tube, and the trap tube is just foliated by marginally trapped surfaces with this property up here, and then it can be space-like, time-like, and the statement is that then you can show that if it is time-like, then in fact the area is decreasing. The same argument that I gave last time to show that if it's space-like, area is increasing, exactly the same argument, just assume it is actually time-like, and just signs flip, and you'll see that the area is actually decreasing as you go to future. If it is space-like, the area is increasing to the future. So what we're looking up here is really the horizons which are formed by gravitational collapse or by merger of black holes. Those are going to be space-like. That is why, for simplicity, I'm just talking about the space-like ones. If you look at quantum theory in which black holes evaporate, then the marginally trapped tube becomes, so marginally trapped tube is just obtained by stacking marginally trapped surfaces, and then it becomes time-like. But for our purposes, we're just assuming it to be space-like. If it is time-like, you can just flip very quickly and see what is happening. Yeah.
So is tau perpendicular to the horizon or just the slice?
No, horizon. Tau is a time-like. You are giving me the horizon, then it's a space-like surface, so there's a unique vector field which is perpendicular to it, and we normalize it by tau dot tau is equal to -1. Yeah.
So just my recollection is that apparent horizon that people define in the literature, it's defined very similarly if it's not the same thing.
So again, I just was avoiding that because we don't need it, but
Okay.
it's good to know about that. So historically, people define this marginally trap. Actually, the definition I gave you about marginally trapped surface was given by Penrose, and that is just a two-sphere, right? It's a two-sphere in the 4-dimensional space-time, which is a property that this is true. Okay. One of the outward null normal is the expansion is 0, and the inward one is negative. Penrose actually had a slightly more general definition, but for our purposes, we can just take that definition. Okay. All right. But then Hawking at one stage thought that it would be useful to use a notion for kind of the event horizon cross section, a generalization of the event horizon cross sections. And therefore, in the beginning, the hope was that, well, we can do it with something which is not associated with the event horizons, just because event horizons are so global and so on. So he thought that, well, what one could do is that one could take a space-like Cauchy surface, and on the space-like Cauchy surface, you can see if there's a marginally trapped surface. And there may be many, in which case you take the outermost one. So an apparent horizon is tied to a space-like Cauchy surface, and it is the outermost marginally trapped surface in this Cauchy surface.
So it's a 2D surface? Yeah.
Sorry?
Is it a 2-dimensional surface then?
Yeah, it's always 2 dimensions.
Okay.
Right.
Since you said it's tied to a Cauchy surface, then I thought so it's different, really. Okay.
It's exactly the same in the sense that the 2-dimensional surface satisfies this. The global property that is coming in is because it is tied to the 3-dimensional slice, because it says that this surface is the outermost marginally trapped surface within that slice. So I might find one, and then I can draw a slice, right? And then I might find but there's another one. Then if I'm interested in apparent horizon, I forget about the first one. I want to talk about the second one. If I'm interested in marginally trapped surfaces, I talk about both of them. The disadvantage of this notion of apparent horizon is the following: that supposing I got an apparent horizon up here, so there's a Cauchy surface and there's an apparent horizon, so this is the outermost one. But now, this of course apparent horizon by definition is supposed to lie in this Cauchy surface and is outermost in that. But what happens is that I could just wiggle this Cauchy surface slightly. And if I wiggle it slightly on the new slice, there may be no apparent horizon at all. So at first it looks like it's good, it's global, it's nice because it doesn't depend on what is happening in the distant future, right? Event horizon is a property that I need to know the space-time topology everywhere. Apparent horizon I don't need to. So you're given a Cauchy surface, either it has an apparent horizon, it doesn't have apparent horizon. And if it has one, then it's essentially unique. I say essentially because it's the outermost one. And you have to define what we mean outermost in a careful way. But then it's unique. Okay. So that was a good idea. But it is still global because it has to do with lying in that Cauchy surface. So for example, I can have up here a marginally trapped surface, and I can have here another marginally trapped surface. And this is outer, therefore I'll say this Cauchy surface is an apparent horizon, it is this. But if I just wiggle this slice slightly, then in the new slice, there may not be any 2-dimensional surface up here that I can draw, which has a property that expansion is always equal to 0, and the surface lies in that slice. Then the apparent horizon here. So what I call as first thought was only a marginally trapped surface with not apparent horizon can change if I wiggle the Cauchy slice. And that's why it is still used, but it is not that useful in proving mathematical theorems and so on. Yeah, please ask him, because I think other people would ask similar questions.
Sure. So if the space-time is stationary after some, does the dynamical horizon become null? Basically, does it merge with the event horizon or no?
So these are the uniqueness theorems. So the statement that it doesn't have to, if the space-time is, but the uniqueness theorem says that if there exists a dynamical horizon which becomes tangential to the event horizon in the stationary or distant future, then it's unique. So it doesn't say that every dynamical horizon should do that. There may be other dynamical horizons inside, for example. But if you like, it is, so heuristically you can think of that in a physical context of the dynamical horizon as being the most used. There could be many dynamical horizons, and the most useful of them would be the one which, when the black hole settles down, this dynamical horizon, then in the distant future becomes tangential to the event horizon. So that is the most useful one. But there may be also inside other ones. For example, when the two black holes merge, right? Two black holes merge, then in fact you can have when they are merging at some stage, they have individual dynamical horizons, but then a common dynamical horizon forms. So that is when the first time the common dynamical horizon forms, that is when one says the black hole has merged. That, at a retarded instant of time, gives it a big burst of radiation in the LIGO signals that you have seen up here. So we have got this dynamical horizon form up here. But I also have these two other dynamical horizons inside the outer one. And they persist for some time. And then what happens to them exactly is actually still being computed and so on. I mean, this is a long topic, so I don't want to go into. Therefore, there can be several dynamical horizons. Two can correspond to the dynamical horizons of, quote unquote, the individual black holes. And the other one corresponds to the merged black holes. So it is not as though when the black holes are merged, in fact, I don't know what happened to the individual black holes. Those dynamical horizons can actually continue for some time. This is the kind of thing that one doesn't see in simulations because they're too fast, but it is actually the case, and the accuracy fails then for these two, the individual horizons up here. But people are doing this very carefully. And there's a very recent paper, in fact, just this month, came out from the Albert Einstein Institute. I think it is Badri Krishnan, Schnetter, and some other people who are doing this. And there's also work by Pablo Laguna's group, which is doing this. Okay, I give you probably too much information. So what we need to know here is that here's the notion of dynamical horizon. I just answered a very trivial algebraic question. Yes, dynamical horizon comes with L and N. And since it's space-like, it also has time like normal. Given L and N null directions, I can normalize them and construct a vector r hat, which is going to be tangential to the surface, and it is unit. And then the area of the dynamical horizon is increasing along this r hat. That's what we show. Now, last time then, we also just quickly finished that part up here. Last time also we arrived at the following equation. Yeah, we looked at our vector field, which was going to be I don't know if I call it C or not. Let me just call it C now. C vector field, which is supposed to be equal to some lapse times NA, and we keep the lapse free in general, and then we just use the fact that I can take a portion of dynamical horizons. This is the portion that I'm looking at now. Delta H is this portion of dynamical horizon. I'm ignoring what is happening in the future. This is what is delta H now. And then I just integrate this quantity. I take the two constraint equations, n times C plus NA times CA times B3B. This is a space-like surface, so this volume element is completely unambiguous. I introduce this. Since C equal to 0 is one of the Einstein's equations, C is sorry. C equal to 0. So the Einstein's equation says that this C is equal to the matter density, which was going to be given by 16 pi g times d by b times the unit normals, and CA is given by 8 by G times T bar AB. So this is the time component, and this is the time-space component. Q is an intrinsic metric on the dynamical horizon. So this is the Einstein's equation. This is a geometrical quantity equal to kind of the momentum density in matter, a geometric quantity is equal to the energy density in the matter. So these were the Einstein's equations, and so we just this is not equal to 0. So we just started this to be equal to this matter density, matter terms. We started with this thing. And then what we showed was that, well, we use the fact that this is foliated by marginally trapped surfaces, and then we arrive at the equation which says that the lapse times scalar curvature. This is the two-dimensional scalar curvature of the marginally trapped surfaces times d3d. So d3d. This was equal to 16 pi g times T bar B. A B H and sigma square so that's the condition. Yeah.
Is that C not plus shift? It's just NLA, or this,
Sorry, sorry.
the sigma, the C, the vector field?
It's just NLA, so this is equal to N times.
Oh no, I thought it had. Oh, okay. I thought it had the plus shift.
Yeah, because N is null.
Oh,
So therefore it has a time-like
yeah,
part
yeah.
and the space-like part. N is just given right here, right? So time-like and space-like.
right. When you write it in terms of the time, like then, yeah, this shift is obvious. Yeah.
So the shift is N times I. The shift is always, lapse and shift decomposition is always with respect to space, the time-like unit normal. Okay, so this is the equation that we're about to obtain. And I just give you the basic physical thing because we are running out of time. This is clearly the flux of the matter density as seen by flux of the matter energy density as seen by the observable C, if you like. Even though C is null, it is a mathematical generalization of the observer. So given by the vector field C hat A has associated with it some energy density, and that is what is falling into the dynamical horizon. And then this quantity up here, I told you last time, is interpreted as the energy carried by gravitational waves. It's like the energy with respect to, we always need a vector field to talk about energy, so CA energy carried by gravitational waves. And I told you last time that this quantity has several properties. First is obvious, it's positive definite, so that's a very non-trivial property. It's not positive definite quantities like this constructed purely out of geometrical fields which refer to just the structure that you are given. This is rare. You don't get it very often in general relativity or even in other general field theories. So you get a positive definite quantity, so that's called. Then you can check that, if in fact the dynamical horizon were spherical symmetric in some little ring, even on a two surface, then on that two surface this quantity will be 0. So again, if it's spherical symmetric, then no gravitational waves. There are many checks that you can do. There's a list of about 6 or 7 checks that you sort of would like to ask about this interpretation, and they are satisfied. In the weak field approximation, this term goes away. Like for example, if you're doing a perturbation around curve, this term goes away. This is sigma squared, and that is what everybody would say is the energy. So there's a good reasons to think about this as being the energy density. So now we were looking at the left-hand side up here. And I just want to elaborate a little bit more on this left-hand side. So the whole idea here was that we look at this D3V, and then it turns, this D3V is just given by, you can just do it by taking the square root of the three-dimensional metric, if you like, and dividing the three-dimensional metric. So the three-dimensional metric QAB we can just write it as a as a two-dimensional metric SAB plus RARB. Unit vectors appear. There's several ways to do it. I think I like to do it in terms of volume element. So if I look at the three-dimensional volume element up here, epsilon ABC, that is just given by 3 times two-dimensional volume element times times R hat B. And now this is the unit vector in the radial direction up here. What we are doing last time, we introduced a radial coordinate, which we said that the area is just given by area of this marginally trapped surface. Area of any marginally trapped surface is just given by 4 pi r squared. So we introduce the notion of the area radius, and therefore I can take dA of r. Area radius, of course, is constant up here. So if I take a 3-dimensional derivative of r, that is going to be proportional to r hat. So therefore, this is going to be equal to dAr will just be equal to its magnitude times r hat. Therefore, this quantity is just given by 3 epsilon AB times r hat, which is going to be equal to dc of r upon the norm of r, which is QAB times dAr dBr to the 1/2. Okay. Which that is to say that is just given by 3 times epsilon AB times dCr upon dr. So that is what we saw last time. We saw that this was given by d2v times dr upon square root of upon, I guess, dr. This square root up here, dr. That's what we saw last time. So that's what we saw last time. So therefore, the idea up here was that, well, n was arbitrary so far. So this equality holds for every n. And so you get a whole bunch of identities which you can exploit, which they were exploited in the papers that I referred to yesterday. But the statement is that for a specific choice, this simplifies. Namely, if I just choose n to be equal to dr, with this choice, and by dr I just mean precisely QAB, dAr, dBr. If I do that, then of course this n cancels with this dr up here that I got up here, and therefore the left-hand side just becomes the scalar curvature times, so this is again ordinate times the two-dimensional metric, the two-dimensional volume element on these marginally trapped surfaces times dr. So r, capital R is now the radial coordinate, and I just get a neat decomposition into dr and two-dimensional integral up here. Therefore, I can substitute. I can do the two-dimensional integral first. So I can write this dr, say from R1 to R2. So this, the first surface is R equal to R1. Its area is equal to 4 pi R1 squared. And the last surface is R equal to R2. And I'm just integrating on that portion of the dynamical horizon. Then I get here dr times integral on the two sphere, R equal to constant of scalar curvature. And tilde just means two-dimensional quantity. As I told you last time, it's a two-dimensional quantity, we have two-dimensional scalar curvature. So we get this very interesting and unexpected equality which relates the integral of the two-dimensional scalar curvature with some matter quantities up here. And now you probably know that the integral of a two-dimensional scalar curvature on a compact manifold is an invariant, a topological invariant. So the statement up here is that this integral is the Gauss-Bonnet theorem, which says that the integral of the scalar curvature times d2v is a topological invariant, and that is just given by, I think it's 4 pi, is it? Yeah, 4 pi times 2 minus 2g. So where g is the genus of the surface. So for a two-sphere, the genus is 0. So it will be 8 pi. sorry, so many people here are not familiar with genus and so on. So if you give me a two-dimensional compact manifold, then you can think of it as a two-sphere with some handles. Right? I can consider a two-sphere, or I can consider a two-sphere with one handle. So this is a two-sphere, and then I got a handle. Now I can contract this handle up here to make it into a donut. So it will look like a donut up here. So it's very easy to do. I mean, maybe with children's Play-Doh you can just do it, right? You just add a handle and then squeeze this down, so it becomes actually a donut. I can have two handles. Two handles. So this will be genus 1. So G equal to 1 is a torus, and G equal to 2 and etc. This is a higher genus. And these are the Riemann surfaces you get. Two-dimensional compact man. So what you notice here is that G equal to 0, you just get 8 pi. G equal to 1, you are going to get 0, because 2, G equal to 1 is minus. And for all higher genuses, you get negative. But we look at the right-hand side. What is the right-hand side? Right-hand side is a stress-rate tensor plugged in with two vectors, which are both future-directed time-like vector, future-directed null vector. I would see what just this is future-directed. Therefore, this quantity is positive. This quantity, by explicit staring in your face, is positive. Therefore, the right-hand side is always positive. Okay, up here. So, I should continue this. Sorry. Okay, the right-hand side is positive. Now we're going to use it. But this, therefore, is equal to this is dr times, so it is going to be equal to, this is a topological invariant, so it is going to be equal to R2 minus R1 times this topological invariant chi of the manifold, of the two manifold. I've drawn the pictures assuming that this is a two-sphere because there's a most interesting case. But in fact, we did not assume anywhere here it is a two-sphere in all this thing. And then the statement is that we find this result up here. So this result immediately tells us something, namely, so long as this positive is positive, manifestly positive, so long as the effective stress-rate tensor times the two future-directed vectors, so long as this is positive, then the right-hand side has to be positive and will be 0 if and only if this term is 0 and this term is 0. Nothing is following across, and shear is 0, and this angular momentum vector is equal to 0. So we get somewhat unexpected result, which says that we already know that R2 minus R1 is positive because we know these two things say that the area is increasing. Therefore, R2 minus R1 is definitely positive. So we get the result that R2 minus R1 times this topological invariant of the marginally trapped surfaces is equal to the matter terms. So 16 by G times times C. Sorry, this is C. I can just C times tau hat A X plus plus the geometrical quantity, which is just by explicit expansion, by inspection, is positive, definitely. Therefore, if this quantity were positive, so this is positive, if in fact you have physical situation that there is either some gravitational wave or some matter falling in there, then we'll just say that chi must be positive. That means topology of S2, topology of the S2 of the marginally trapped surfaces is S2. And that is why we're just focusing from the beginning on S2. We didn't have to. We could just let it to be an arbitrary compact surface, carry out this whole analysis. It doesn't care about what the topology is, just worries about the fact that it's compact. And then we arrive at the result then in fact in physical situations the topology is actually that of a torus, and it will be that of a two-sphere, and it will be torus genus 1 if and only if each of the terms, so if torus, if the right hand side, if this quantity vanishes, right? If d bar AB d3x plus this positive definite quantity equal to 0. In other words, this quantity will have to be negative and precisely balance this quantity. Then it will be torus. Right? And it will be, this chi will be negative, so it will be higher genus if and only if this quantity is negative and overwhelms this quantity which I got on the right hand side. Okay, so what is T bar AB? Remember, T bar AB was equal to TAB minus lambda 1/8 pi g times GAB, where lambda is a cosmological constant. So if I take TAB, T bar AB times CA tau hat B, these are both future directed, that will be equal to TAB times CA times tau hat B minus lambda by 8 pi g times the contraction of these two things. But the contraction of these two things we just see here is just going to be L times C is just given by N times L, and then the contraction of tau with L is just equal to -1. So we see that that is equal to minus N. So we see this quantity, this is the answer we have. And therefore we see here explicitly that if lambda is positive, the cosmological constant were positive, this quantity is necessarily positive. Even if there was no matter term at all, now we are going to assume that energy condition holds. That an energy condition just implies that this quantity is positive, non-negative, and is 0 if this quantity is non-negative for energy conditions. Therefore, this quantity is non-negative, and the cosmological constant is positive, and this is definitely positive. And therefore, if lambda is bigger than 0, then this quantity is positive. So, in the case when the positive cosmological constant, the torus topology cannot occur. The torus topology cannot occur, higher genus cannot occur. The black holes will have only topology of a two-sphere. If cosmological constant is equal to 0, cosmological constant is equal to 0 up here, then if lambda is equal to 0, then the statement is that this quantity that we're talking about, chi, can be positive, if this is equal to 0, and the energy condition is satisfied. So this quantity can be actually positive, or could be 0. So if lambda equal to 0, the statement is that we got the two-sphere topology or torus. Either of these topologies are allowed up here, but torus is really exceptional, because if it is torus, then the gravitational waves term should be 0. There should be no gravitational waves falling into it, and furthermore, there should be no matter. So T bar in this case, lambda equal to 0, it's just equal to T. There should be no matter energy also falling into it. So it's a very, very, very special balanced case. So this is really, special degenerate case which will not occur in nature, but it is mathematically allowed up here. But if lambda is negative, then all bets are off, because if lambda is negative, this quantity is negative. Therefore, even if I have positive matter, this can be negative, this can be positive, this can overwhelm this, or this term is always positive, and this term is negative, this term is positive, so I cannot say anything. Therefore, here, all topologies are allowed. And somewhat surprisingly, if you look at the literature, right? I mean, not surprisingly, I mean, as you might expect, if you look at the literature on black holes, of course, these are dynamical horizons, but you think of these dynamical horizons as being, I mean, black holes, stationary black holes, as being formed by some process in which there is a dynamical horizon, which then becomes asymptote to the event horizon, the killing horizon. So if you look at the stationary solutions to Einstein's equation, then of course lambda positive or lambda is equal to 0, the topology of the horizon is always that of a two-sphere. But if lambda is less than 0, then in fact people have found black hole solutions, even in 4 dimensions, with other topologies. And that is allowed because of this equation. So this is kind of, to me, a very beautiful example of this interplay between mathematics and physics. What is the topology of the surface of a black hole is answered by using Einstein's equations together with geometrical considerations, and we see that it can be any of these cases for lambda less than 0, lambda equal to 0, or lambda positive, which is physically most interesting. Then the statement is that the topology that is allowed is only S2. And that is why we're focusing on S2. Okay, so this is the end of the black hole thing, and please ask questions. Yeah.
But this is strictly speaking just for dynamical horizons. I mean, we're not talking about the topology of event horizon. Let's say there is no stationary region in space-time.
Right. So the statement that for the event horizon, I mean, there are no solutions, of course, known which are not stationary. Even in lambda. So the statement is that, yeah, so if you have event horizon, then the statement is that there is another theorem due to Hawking, which is something else which is completely different from this kind of theorem, which gives topological restrictions on the topology of the event horizon. This argument does not tell you anything about that. This argument just says that if in fact the event horizon was formed by this collapse, so there was dynamical horizon which settles down, therefore by this uniqueness theorem became actually the event horizon. If the space-time admits event horizon, then it will be the event horizon. Then the statement is that the topology of that event horizon is 2. It doesn't say anything about the topology of the event horizon. For me, dynamical horizons are much more physical, and this is what is talking about dynamical horizon or the isolated horizon that will be formed. They may not be stationary.
Yeah, and here you are assuming that the difference capital R2 minus capital R1 is positive, right? That is crucial, no?
Right. So we are using here critically the fact that it is actually a space-like surface.
Right. But that's the question. Is that what you are assuming here is that the dynamical horizon is growing, right? Or not?
No, that we proved that last time.
That follows from
This
definition.
comes from this definition. Space-like and these two things says the dynamical horizon is growing. Maybe your question is about marginally trapped tubes. That may be.
Because I was thinking that if you don't have any flux of gravity waves, matter, anything, the dynamical horizon will not grow, will essentially stay. No?
Right. So then it will not be space-like either.
Okay.
So it will become null. So then it will be the. Any other questions? Last chance to ask questions about black holes. Okay.
On the right, about the equation of motion from
The equation of motion of what?
for the variable associated to the addition QE, let's say.
So the question is, can we say something about the equation of motion within the dynamical horizon?
Yeah.
Well, dynamical horizon is space-like, so you can talk about equation of motion in the sense that this equation is satisfied, this elliptic equation is satisfied, and therefore you have a.
Taking the Poisson bracket of the two equations with Q, what would I get?
You'll get X is determined. You know what you get. But
So
Well, that's the Hamiltonian.
sorry.
It's a NC plus NAC, basically Hamiltonian. Right?
Yeah. Okay, you asked it. I don't know what your question is. So the statement is that this is a space-like surface. This is a Cauchy data. So if you want to do time evolution in going in the direction of this time up here, then you will of course get you'll get this is the Hamiltonian which will evolve along the direction L. Along the direction L here everywhere. There's the direction L. Sorry, the direction L that is going to be evolving in. So I'll get another surface. That surface is not going to be dynamic in horizon because it's not going to be marginally trapped. The surface will be trapped up there, but you will get the same equation. Einstein's equations are just the same. It doesn't make it.
just curious.
All right.
Something special.
Okay. So now the next topic that we are embarking on is gravitational waves. And I would really appreciate particularly people who are taking the course to tell me whether the remaining time we should divide roughly equally between gravitational waves and cosmology, or whether we should divide it differently, more time in one, less time in the other. Please let me know, please send me an email, or just tell me after the class what you prefer. And I will try to adjust the course according to the majority wishes. If you don't have wishes, then I will do it. I will just make a choice myself, okay? Okay, so this is the second part of the course now. Now, prerequisite for this course is GR1, and so I'm going to assume that everybody has seen gravitational waves in linear theory, linearized approximation, things like quadruple moment formula, something like that. So I'm just going to assume that. And our focus here will be, what do we mean by gravitational waves in full general relativity? When people show you, like last N lectures, waveforms in LIGO, what the hell are they plotting? And so, you know, what does it mean that they are seeing gravitational waves? What quantity is that is actually, I mean, being plotted up here? So that's what we want to understand up here. So this is a broad topic. So the first part of this is just going to be Maxwell theory, or electromagnetic waves. And even in Kasper space, although everything I'm going to say generalizes to the to asymptotically flat space-times. I'm just starting with completely familiar territory. Everybody has taken course on Maxwell equations in flat space-time, and if we just want to examine it, recast it in a certain way, that will go over to the full general relativity, right? I mean, that's the whole idea here. We are going to isolate mathematical structures, various fields, and develop intuition for what information lies where. Where is the information, for example, that is relevant to the gravitational wave detectors? Where is the information of the energy that is carried by gravitational waves? People told us many times that in the first, immediately after the black hole collision, the energy that was radiated away exceeded the energy that is radiated in all stars in the universe. What the hell is that energy? So that's the thing that we would like to understand here, we would like to calculate here. Where is it? How do we calculate it? Then other people tell you that, well, when the black holes collide, the final black hole can have kick, because it will be like a rocket effect. It could be that the merger is asymmetric and sends out gravitational waves, a lot of gravitational waves in this direction. So it's like, you know, a rocket throwing the fuel, and therefore the final black hole is going to move in this direction. And how much kick does a black hole have? Do they get kicked out of the black galaxy? And this was a hot topic a couple of years ago, maybe 3 years ago now, and it's of astrophysical relevance. And the question that I would like to ask is, well, that's all fine. You can draw those heuristic pictures, but what are you calculating to draw those heuristic pictures? What does it mean to say that the 3 momentum carried away by gravitational waves is large, and therefore the black hole should move, you know, in the other direction? What is it that we're calculating? So these are the questions that we want to ask. And how do we distinguish between the information, which is such as the energy carried by gravitational waves, momentum carried by gravitational waves, and for example, what a satellite sees? If I got a black hole, and you know, black holes are colliding, then also supposing I got a faraway satellite, what is that satellite going to see? Or what is going to dictate the orbits of this? In other words, where is the Coulombic information in the gravitational field? Where is the radiative information in the gravitational field? So these are the questions we want to ask, and then the Maxwell theory provides a very nice arena to answer those questions. So that is why we begin with Maxwell theory. So everybody knows about Maxwell's equations, so we just start with that. So Maxwell's equation to begin with. It is df equal to 0, and df equal to 0, and usually people write this equation as, which is the same as c equal to 0, and then the other equation is about grad A of bracket B is equal to 4 pi. It's 4 pi JB. There's a current density. These are the Maxwell's equation. It's always amazing, right? That you just write down this equation that is explaining everything from how much light is being emitted and so on, starting from the jets, the black holes to the light that is in this room up here. It's all here. And this J is the source current of this Maxwell equation. But I can also write this equation, and this I can just leave it as an exercise, as d of star f is equal to transfer sine Flux 4 pi times star j, where star j is a three form. This is a three form, so therefore that is a three form, and that is just given by epsilon d abc. So this is a three form. So we usually think right of the current as a vector, but I can just use the epsilon tensor in space time, take its dual, and then. So this is really this is really just the dual of the divergence. The dual of the divergence is exterior derivative of the dual of the Maxwell field up here, and here I'm taking the dual of the current up here. So these are the equations I have. Now supposing I actually have some source current up here, so I got here J or J star. Doesn't matter. J or J star. Here I got current density. So J star in BC. And now I would like to calculate the solution. So typically we calculate a retarded Green's function and the field propagates it using retarded. You can calculate retarded. I mean, this is something that you have done many, many times. So I don't want to go into it in great detail. So one other thing that immediately happens is the following. That these equations, Maxwell's equations, are actually conformally invariant. So let us understand what that means. And this is why it is mathematically very easy to treat Maxwell's equations at null infinity, and then we'll get intuition, and then we'll go on to gravitational waves. Einstein's equations are not conformally invariant, and therefore we have a little bit more work to do. But Maxwell's equations are conformally invariant, therefore life becomes very, very simple. So Maxwell's equations are conformally invariant. So what we are interested in doing is the following. We are interested in what happens to these fields as they go out to infinity. So we are interested in radiation, and you have learned from your electromagnetic courses that this radiation is always going to be like 1 upon r. So we are interested in the 1 upon r fall off of the Maxwell field. And the Maxwell field, the waves are going to propagate in null directions, and therefore the idea is that the structure would simplify if we actually compactify space-time and have Scry. We are only interested in Scry plus, we're not interested in Scry minus, so we want to know outgoing radiation up here. So I get here Scry plus, and here I got Scry minus, and I'm really interested in what is happening up here as the radiation goes to Scry in the directions. What happens up here? And heuristic idea is 1 upon r. I'm just telling you the physical ideas to motivate, and then we're going to see precisely how the mathematical framework captures these ideas, and in which sense it does not capture these ideas. So that's what we're going to see. So we're going to use this conformally invariant strongly, because as you saw before, that we can write down the physical metric as I can introduce a coordinate so that these lines are retarded lines, u equal to u naught. So u by just take to be t plus t minus r, then dA squared. Minkowski metric just becomes this minus twice du dr plus r squared times d omega squared, the two sphere line element up here. And u equal to u naught are these null lines, and this is what we're going out to infinity. So, and then what we do is we just do conformal completion. If you remember from our first lectures on black holes, when we introduced Scry and we went and the event horizon notion, that I just define this to be equal to omega squared and times dA squared. And omega we took to be equal to 1 upon r outside some spatially compact for some r bigger than r naught, some spatially compact region. And inside you can take whatever you want. It doesn't matter because we're only interested in the structure out at infinity. So if I did that, then this dA squared simplifies and that just becomes minus omega squared du squared plus twice du d omega plus d omega squared. So this now becomes just the unit 2 sphere metric, which is d theta squared plus sine squared theta d phi squared. And this is just the du d omega term. At scri itself, omega is equal to 0, so you don't have this, but the 4 metric is still non-degenerate because we have got the term du d omega plus omega squared. But the important thing is that the angular part will now become, this angular part up here we got at scri is really a unit 2 sphere metric. Just want to recall that. This is a unit 2 sphere metric. Okay. So we want to work with this space-time, and we want to know what is happening to the Maxwell field at infinity. And from there, we'll read out all this information. Where is the information about the waveforms? Where is the information about the energy density, energy carried by electromagnetic waves, momentum carried by electromagnetic waves? And there is information about the charge of the source. And the nice thing is that at scri, all this information unpacks itself. In the interior of space-time, it is all muddled in FAB, but at scri, as we'll see, various components of the Maxwell field carry different information and structure becomes transparent. And that is what I would like to see this lecture and the next, in the beginning of the next lecture. So we're looking at this conformally. So because this metric is conformally obtained from this metric by conformal transformation, we would like to understand the conformal properties, conformal transformation properties of Maxwell equations. And the point up here is the following, that this, so if I set, I just define this, f hat AB, so we have g hat AB equal to omega squared times GAB. G is the physical metric, the Minkowski metric. G hat AB is a rescale metric. I don't write eta AB because almost everything we do is really true for general asymptotically flat space-time. For concrete expressions, I might often refer to Minkowski space, but it's not necessary. So, like I did there, but it's not necessary. G hat AB is equal to omega squared times GAB. Then what happens to epsilon ABCD? Well, you can easily check that if I take epsilon ABCD with 2 down and 2 up indices, then that actually is conformally invariant. That does not change. The epsilon ABCD with downstairs indices gets omega to the 4th factor, with upstairs indices get omega minus 4 factor, but 2 up, 2 down is conformally invariant. So now, if I just define f hat AB, I just consider f hat AB to be equal to FAB. I didn't do anything at all. Right? Well, if f hat AB is equal to FAB, then of course star f hat AB, which is given by 1/2 epsilon hat ABCD f hat CD. Well, f hat is equal to f, so this is f. Epsilon hat is equal to epsilon, so nothing changes. So therefore, this is equal to 1/2 epsilon ABCD and FCD, and then therefore it's f. So if I don't rescale f at all, that is what we build the conformally invariance, then if f is equal to f hat, then star f is equal to star f hat. That's what we just showed. But here our equation was that grad of FAB equal to 0. So the first our equation, but we know that 0 is equal to grad A of PC. But f is the same as f hat. And I think you all know that the exterior derivative doesn't depend on the choice of the derivative operator. It doesn't have to be a covariant derivative, it can be any derivative you choose here, it can be coordinate derivative, anything of that sort. And therefore, in particular, I can use this to be equal to grad hat. So what we just showed was that because f is closed, because f satisfies df equal to 0, f hat is also closed. F hat satisfies this or this equation. So this also satisfies the first Maxwell equation is also satisfied by. So what we've shown is that this implies that grad hat A, hat BC is actually also equal to 0. So if you like, I give you this field, Maxwell equation satisfied, and in one side I say I got the metric G, and the other side to two students I give you metric G and a G hat, and you could not tell if in fact which metric I'm using to do this Maxwell equation. It will satisfy the Maxwell equation with both those metrics. There's no problem. And now the statement is that the same thing is true here. These are just df and df. If f is equal to f hat, df is conformally invariant. So if f is equal to f, but on the other hand, we saw that star f is also equal to star f hat. Therefore, not very surprisingly, this equation is also conformally invariant. Namely, we just get here d of star hat is equal to 4 pi j, 4 pi times star j hat, where here star j hat is equal to j. We don't change anything. It's pretty remarkable when you write it in under these three forms. You don't have to rescale anything. You can think of this as this current three form as living in the Minkowski space, or you can think of it as living in the conformally completed space-time. You can think of this f as living in Minkowski space, or you can think of it as living in a conformally completed space-time. Now, why is this relevant? Well, it's relevant for many reasons. Because we are interested in understanding the structure here. And here, the metric G hat AB is completely well defined. But the metric GAB is not well defined because I got factors like R squared here, which blow up there, so the metric is not well defined up here. R is not a good coordinate, R is equal to infinity. Omega is a good coordinate. Omega is this infinity function in the neighborhood of scribe here because this is just omega equal to 0. So I'm just doing expansions along omega equal to 0 and coming down up here. And here, as you saw, this is a unit two-sphere metric. So this metric is perfectly well defined near scribe, right? In the neighborhood of scribe, no problem at all. So what I can do is now, I can say that I got the Maxwell equations. So I got the Maxwell field at E satisfy Maxwell equations on the conformally completed space-time. If you give me physical Maxwell field in Minkowski space-time, then I just set f equal to f hat equal to f. It satisfies Maxwell's equation in the conformally completed space-time. But this has a very strong consequence. Namely, in the conformally completed space-time, scri is just a finite surface. Right? If you think of this as being space-time, and here is my source going up, doing something, right? This time is running like that. Then the conformally completed space-time, scri is here, right here. It's not at infinity, it's a finite distance. Because here omega is equal to some value, like 17 say, and here omega is equal to 0. So there's no problem at all about, I'm just going a finite distance away with respect to the unphysical metric and with respect to the conformally rescale metric. Now if I told you that I have a source up here in this room, right, and I emit it's emitting these waves, and I say, well, I'm interested in this null cone. So this room is to be thought of as time running this way in space like that, or other space-time. And I got null cone up here. But of course, the field is smooth, right? The Maxwell field that is emitted is going to become perfectly smooth on this null cone. So therefore, there's no question that because I got these solutions, I'm looking at retarded solutions, this is a finite surface, therefore it's obvious that f hat AB is smooth. Okay. And now this all seems very trivial, but this is what gives rise to the Peeling theorem. I hope to do that Peeling theorem today, but we don't have enough time. What Peeling theorem tells you is that various components of the Maxwell field fall off in different directions if you expand the Maxwell field in the Newman-Penrose tetrad. And therefore you can find the components which fall off like 1 upon r. They carry information about radiation. I can find component which falls like 1 upon r squared. It's all sort of, the leading order piece is beautifully encoded, exactly some fields ascribed here. And I can use that field to calculate the electric and the magnetic charges. And those of you who sort of follow things in the literature, in quantum literature, the soft magnetic charges, soft electric charges, you can all calculate them using the fields up here ascribed. And finally, you can express you can see that in fact, the free data on SCRA, in other words, I got this FAB, F hat AB, it satisfies some field equations, but then which part of F hat is freely specifiable and which part is really dictated. And we'll see that there are exactly 2 functions which are freely specifiable, and therefore these are the 2 radiative modes of the Maxwell field. These two functions are called phi2 not 0, and that is where the radiation information is. The reason why they are radiative modes is because they are completely freely specifiable. Other components of Maxwell field, their time evolution is determined by what you specified for the field phi2 0. And therefore, if you have a Maxwell field and if you wanted to plot what is the field strength, or you wanted to have a plot of the radiation, then you'll plot phi2 0. When we go to general relativity, the structure is completely parallel. What is different is that the proof doesn't go through because the equation is not conformally invariant, so you have to work much more harder. But at the end, again, there are 2 functions which are freely specifiable up here, and these are, and other components, the Y tensor, are going to be completely determined by these 2 functions and some boundary conditions. But boundary conditions are specified at minus infinity as scri, but or scri. Dynamically, only 2 functions are free. And then the statement is that these functions is what we call the radiative modes or gravitational waves. And then this is precisely, in Maxwell theory, it is, as we are going to see, it's the phi2 naught component of the Newman-Penrose component of Maxwell field. And for gravitation, it is psi4 naught component of the gravitational field. So I'm building this up so that we can understand the structure of the gravitational field very well. Here we know everything, right, for Maxwell field. We've got a stationary tensor, we calculate energy, we can calculate everything. So here, our job is really to take known physics and write it in some language, which then goes over to gravitational waves in a direct manner, and therefore we can carry over our intuition there. Okay, all right. I think we should just a second.
Yeah.
Anybody who wants to leave, please leave, but we can continue talking.
Just a small comment for clarity, the star J hat, you mean star J hat equals star J, right?
Thank you. Thank you.
And
Thank
then
you, thank
also, again.
Please, I appreciate you correcting these things because it can be very confusing for people who take notes.
So as a comment on that, what's the assumption that's going into J that allows that condition to hold?
No, so the statement is that I'm just assuming that the J, right? I mean, so I'm just saying that, well, I define this is the right-hand side of the divergence of F. Okay, so that's given to me. So if you like right-hand side, J is just minus 1 upon 4 pi times divergence of J. Like that's what is given to me. And therefore here, I'm just assuming, so if I, right, so therefore I now calculate G of star F. So from here I can calculate, yeah, I did calculate somewhere, right? Yeah, I did calculate. I did calculate star of D of star F. D of star F doesn't change. So I calculate J. So the statement is I calculate star J, which is here. So I calculate star J like that. And this equation requires me that this be conformally invariant. That tells me that this should rescale like omega to the minus 2. But it's not that I'm assuming that. I'm arriving at that by saying that if I wanted to use a current, then this rescales. Yeah, so.
Yeah, I just think that's a non-trivial statement.
It's a non-trivial statement, but on the other hand, in the beginning I thought that it might be something more. I mean, the non-triviality of the property is that it is just conformal rescaling of the vector field within the source. It doesn't change the support of the source. Right? And so it is whatever it is with this. I can choose in the source omega equal to 1. Because I just need. So it has no. It's true that mathematically you have to specify that. But I choose to specify Maxwell's equations not like this. I wrote them like that just because most people in the class are familiar with this. I choose to write them like that, and I just say that, well, there is some star j, and I just keep this star j the same. And just like, so if you like, it's not trivial that epsilon ABC downstairs picks up omega to the 4th, whereas this doesn't pick up omega to the 4th. It's no more non-trivial than that.
If instead of the dual of j as a vector, if you specify j as a vector itself, then that's not the same on the conformal transformation.
Right, it's not the same. But the same thing is true. If I take FAB, it is not conformally invariant.
But in defining f, we don't really need metric.
Right.
So
And to define star j, you don't need a metric either.
right.
Because star j is just the right hand side up here.
I mean, the left-hand side is completely, essentially, metric-free, because you're taking the exterior derivative of f.
Right. And the right hand side is also star j. If you,
Right.
if you were to cleverly give me what is star j, you're not used to it, but that's your problem. That's my problem, but that's our problem. Well, you are, I don't know you are. We're not used to specifying star j, we're specifying, but
That's
that's
true.
just our problem.
Yeah.
Star j is what you should specify.
I mean, whenever you make epsilon d a b c, that kind of in local coordinates depends on the metric. If you write, so that definition does become a metric.
Right. So what he's saying is that this epsilon with this index structure only depends on the conformal class of the metric.
Yeah. So that makes.
So that's what he's saying.
Yeah.
Yeah.
Okay.
You didn't mean anything else than that. That this is you're completely right. This epsilon ABCD is tied to the metric. The downstairs or upstairs. If you just consider this object, this is not conformally invariant, and it is absolutely tied to the metric. And this also is tied to the conformal class of metrics. It is still not completely. Yeah. So in the universe of conformal class of the metric, this epsilon is the same. With that index structure is the same. So star operation is conformally invariant because it uses epsilon with 2 down and 2 up indices. Anything else? Okay, so we'll meet after the spring break on Monday.